gaming situations, you can also use it as a source for driving a mouse or changing a keystroke to interface with some aspect of your software. So it requires, of course, some level of signal processing, and then also some classification needed to understand exactly what part of that signal is triggering what parts of the game, whether it's a magnitude threshold that's crossed that triggers some sort of response, or if it's a frequency content change that has occurred that may need to trigger some response in the game itself. And you can imagine there's some neurological conditions where what you're trying to do is maybe reduce co-contraction or increase overall motor units recruitment and increase firing rate. So you could look at decoding different frequency signals or different frequency content of the signal, and or looking at magnitude changes as well. So some of the clinical problems that can pose a design challenge for this, specifically for these examples that I'll show you, have to do with muscle contractures. So children with cerebral palsy, sometimes post-stroke victims as well as, or stroke survivors, and then also folks with traumatic brain injuries, they will often have a situation where potentially the wrist is in a contracted situation where the flexors are always contracted and they can't open up the wrist to then manipulate the objects around them. So this can be a very debilitating condition for someone, both for hygiene to maintain their health, as well as feeding, as well as opening doors, any number of things, writing in school, everything. So some of the challenges then that come from that is how do you open up that joint? How do you open up the system so that it's not in an overly contracted kind of unusable state? Other ways it can pose challenge here is that if someone has a condition that has restricted the range of motion because the joint has been immobilized due to some fracture or some soft tissue injury that has had to be casted and kept in this position for a long time, you may need to regain full range of motion and strength to perform the tasks that you want to get back to. So this is maybe unrelated to these more neurological conditions. And then finally, nerve damage can happen in any number of ways that can restrict the ability for the person to both sense what's going on as well as control it. So providing some very focused rehab in that space can give some application for these games. So EMG signal can be used as feedback in a very rudimentary fashion. Just display it on the screen for them and give some target, some line that you need to hit for the magnitude. So it can be used as a nice feedback tool, and it has been used as feedback in physical therapy practice for a long, long time. But it typically was initially used as an auditory feedback where the signal would make some sound, either a number of beeps or a change in tone of the beep to indicate intensity. But then also you can visualize it by just plotting in real time what the actual graph is. So this can be done with an oscilloscope. This can be done with a quick analog to digital converter and then displayed on the screen. With the recent technology developments, it can also be done just wirelessly to someone's phone or to somebody's tablet screen. So you can do things such as showing the person what you expect them to do versus what their actual activation level is. You get some feedback in that regard. So that raises some questions about what's the best way to show the person this data. You show them raw data that's totally unfiltered. It's easy to get quickly on the screen. And this is then a continuous signal that they're looking at, right? But as you know, if you've seen any of the graphs that we've shown you this week, or you have experience already yourself, EMG raw looks very noisy, right? It looks maybe like something that's hard to interpret if you have no experience with it, like these patients would. So maybe you filter it, but it's also a continuous feed of data at that point. But maybe it's fully in a enveloped form or fully low cutoff frequency for signal processing filter. And then otherwise, you may just say, make it a threshold display where it's only shown if it crosses a certain threshold, that it's shown as a binary sort of response. Like you haven't activated enough, now you have. Or some nominal variation of that as well, where you activated enough, but 50% more gives you another sign, 100% more gives you another sign. So you can scale it to be a nominal and binary sort of approach. And then other questions about the best practice is, do you show it to them visually, or do you give some tone, or do you give some haptic feedback as well? So is there some other tactile response the person may respond better to? So it depends on what sort of interaction you want to have with the person, right? If you're trying to give them active cues while they're walking to give some haptic response, maybe there's a vibrotactor in the prosthetic socket that is giving feedback. I know some people in Delhi who are doing this. Or maybe it's something that gives some tone to them with some earpiece that they don't have to have a visual display in front of them, but they can get feedback some other way. Or maybe they're in the clinic or at home looking at some visual display that helps them to better understand whether they have good control of the muscle or not. So when people started looking at this in classical physical therapy practice, you started thinking about, well, if I'm using feedback as a mechanism for therapy, it needs to be tailored to what type of patient it is. So the older adult is going to respond to a different sort of feedback than a child who's 10 years old, just based on their life experiences, based on their willingness and ability to interact with technology, based on their willingness and ability to play games or please the clinician by matching some line and going back home again. So it has different perspectives that they bring to the therapy. Also, you need to consider what's the cognitive capacity of the patient. So we might assume that they'd be willing to entertain any sort of interactions because that's what we're willing to entertain. But if part of their condition also has affected their cognitive ability, you don't want to make a stressful situation or some situation that they won't even be able to necessarily comprehend what the cue is or what the command is or what the point of the therapy actually is. So making a tailored interaction is perhaps a strong goal. And then how to keep their attention versus having things that are distracting to them. So if you start designing games for children, you can put any number of graphics in there that you want, right? And that can be exciting. You've got spaceships coming in, you've got aliens, you've got things that you need to lob, fruit at, whatever. But what part of those things you want them to have their attention on versus what things are maybe going to be too distracting for them. And then on the other side of it, do you want to build in distraction? So to challenge the space a little bit more, so they're very focused on this one thing, but as a distraction cue comes in, can they stay focused? That kind of level of therapy that might be interesting to consider, or another level of the game itself. So some of the challenges for making applications of this is the density of the data. So do you give just a single channel of muscle activity, or do you give a couple different channels, or do you give more than a couple? Like, do you give 4 channels, 6 channels of information? Interestingly, most of the applications that we're going to talk about today have to do with the agonist and antagonistic relationship between 2 opposing muscle groups. And so do you show both of them, or do you show a ratio of activation? So in other words, do you show both signals at once, or do you just show a ratio of the signals, or do you show some inversion of that? Other ways that this has been shown to be useful as feedback is if you have a series of muscles. In this case, these are 3 of the quadricep muscles, and then 2 of the tricep, or I'm sorry, 2 of the hamstring muscles. If you have these 5 muscles here, you can plot them out in kind of a polar mapping structure to show a relative activation based on how much torque the person is producing at any one time or what directional specific task that you're giving them. So you can map out situations where you have, sometimes we've done this where we have muscles that both radially deviate and then ulnarly deviate and flex and extend. And so you can have basically muscle in each corner and then give the person a different kind of task on that polar map to meet and see which muscles activate and which muscles co-contract to resist that. So you can map out a sequence of things and then figure out how to make a game out of that or some sort of feedback that could be interesting for someone. And then the last thing is, perhaps the most important after all of these things, is ease of use. So if you think about making something that works in a clinical environment, it needs to be something that's able to be set up very quickly, that the therapist can use and not have to, calibrate, restart the thing when it doesn't work, that they can put onto the patient very quickly. The patient just doesn't take off right away because it irritates them. In the home environment, that's a different thing altogether. You have unsupervised use, right? So if you have a therapeutic tool that you send home with the patient, It needs to be robust so that when the little brother sits on it, it doesn't break. That when the dog chews on it, it doesn't break. You need to have something that's very robust, but also works well without having the therapist there to tell the patient what to do. And then, of course, this maintenance of these systems is always going to be a struggle no matter what you devise. So when we've looked at this and compared our work has been compared to a few other groups' work, first thing you want to consider is what dimensionality of the game even would you want to use, or what sort of platform do you want to work within. So your options are, you can make something that's a coordinate-specific play. We have an XY plane. You have to go to a certain spot and direct your muscles to activate the mouse to go there. Or you can have, in one case I'll show you just a bit, a one-dimensional interface where it's more of a magnitude controller or a threshold controller, but then you have the x-axis. X-axis as like a time scroll. So I'll show you a game in just a moment. It's a very simplistic game. You may have played even in your time when you should have been studying instead, where the terrain rolls by and the thing is just going up and down, right, flying through space. So it's really just an x-axis, or sorry, a y-axis controller, but you have an x-axis interaction as well. And then also whether you have things that are directing the game based on just one single input or a multitude of commands that can control the game. So the first case I want to tell you about is from a paper. It's been a while now since this came out, but this is a group from the University of Washington that was in a PT department, as well as some interaction with some electrical engineering faculty. And they developed this idea of the first, probably the application of neurogain therapy for children with cerebral palsy. And so in pediatric work, sometimes they'll actually list the patient's names, which is kind of strange to me. I guess we don't know their last name, but it is interesting because it gives more of a human aspect. It's not just patient one or subject one. It's someone named Alex, so somehow you feel more human connection to this individual, which is more common in pediatric literature. I've never been able to get used to it myself. It seems a little strange to know the person's name. Maybe they made up the names. I don't know. So some description of what they are. They are children with cerebral palsy. They're these ages and what their actual diagnosis and condition is, which arm is affected, what level of clinical evaluation, the severity of conditions are there, and then all the other things that a clinician might want to know about them, which we won't go into. What they designed was basically a two-channel system that was collected to this small thing that they call the neurochip, which is a clever idea, but perhaps not very descriptive, where you basically have two channels of EMG coming in, and they would pump that value out into a controller for this game. And not a lot of detail given here, of course, but what I want to show you is this is essentially an XY axis controlled game where they were manipulating the direction of where the object would go in this space by having the flexors and extensors make it a rightward movement or a leftward movement. That was pretty much it. And then the mouse was controlled by the non-affected limb as the mechanism that would hold and grasp things or drop it. So they could grab onto a ball, move it to some spot, and then drop it by letting go of the mouse button. So it's a way to have two forms of interaction with the game with two channels of muscular control as well. And so their approach was to try to restrict how much flexion there was in the system and free up how much extensor activity could happen. So there's two different approaches that they went through. We'll go through just this first one here, where they had an initial assessment of the patient's ability to control their flexion position as well as their extensor activity. And then they actually begin to assess their ability with the game. So they take 2 weeks of training in the PT clinic, and then 3 weeks of home therapy using the game while they went home. And then assess them a week after that, and then another week after that. And so very briefly, what you see, this is saying that they are able to maintain activity without antagonistic kind of interference. And then what you see is the 4 patients along here. So this is early, in fact, day 0, and then day 15 of game practice. So if you see an upward slope or a positive slope, that means that they're improving in this measure, correct? So the authors in this case found that Alex, Chris, and Danielle all had what they considered to be noticeable / significant improvement over those 15 days. But they found that Brittany was a little bit scattered and not quite improving in a way that they would consider to be significant. And then this one, the y-axis is maximum extensor activation. So this is trying to directly show how much improvement there is in the ability to control the extensors, not only just resist the antagonistic activity of the flexors, which were the ones that were under contracture. And again, they said that they thought this was an improvement, this was an improvement, this was an improvement, but this was not an improvement. So for whatever reason, it was not working for the second patient to get as much improvement as they thought was necessary. However, you could argue there's still an upward trend in these cases, at least in this one. So then the other thing that they looked at was active range of motion. So in each of these patients, pre-test to the second post-test, you see in general an increase in the active range of motion for this patient. Actually, yes, it went from, I don't know why this is negative right now, actually. But then more importantly, this phase here is kind of grayed out. This is the 5 weeks of intervention when they weren't being assessed. And so they wanted to see what was the effect of just being tested twice, and then what was the effect of being tested twice after the intervention. And were the changes sustained or not? So you can see in this case, there's maybe a slight rise in their ability to have active wrist range of motion, and then a slight decrease 2 weeks after the intervention is over. So it's a little bit unclear if this is something that stays with the patient for a very long period of time or not. This person saw a greater increase, but also a greater decrease 2 weeks after. These scores are a clinical assessment score of an upper extremity kind of utility score. And so you see maybe no effect for this person, maybe no effect for this person. Interestingly, some increased effect 2 weeks after for this person. And this individual also had a 2 week kind of after effect as well. Okay, I'll skip forward a little bit. So overall, what they found was that patients completed during this 5 week therapy session, an average of 8.5 or 8.8 hours of neurogame therapy during that time period. And so that's how much investment or time they had with the device, right? So it wasn't like they were playing day in, day out. They were just playing as small amounts, but in therapeutic regimen, about what would be expected. This statement here, the patient showed great improvement. This is the claims of the authors of the EMG activity during gameplay, shown in the form of increased extensor activity and decreased co-activation. So that would be a clear win for the therapist to know that that is improving. And then the other thing that they claim is that several patients improved in functional measures after neurogame therapy. But we saw from those previous slides, maybe that's a little bit arguable as to whether that shows a solid improvement or more of a transient effect from the therapy that maybe is starting to go away 2 weeks later. But with that, they saw increased range of motion, decreased co-contraction, which is the same as decreased co-activation here, and increased upper extremity function. So at the end of all of this, the clinicians often are only worried about the functional scores that come from these measures. But the PT also in the middle of therapy might be interested in active range of motion, as well as how much co-contraction that has been reduced. So it's a little bit mixed as to the result of this particular intervention. But again, this is one of the first studies to come out and show this is a designed interface between the child and the computer that we can control a game with. They're more interested in actually their own technology than the outcomes of the study clinically. And that led to other studies that showed more and more clinical efficacy after changing the play of the game and changing the therapeutic regimen. So this was a little bit more of a proof of concept paper. All right, next thing I want to tell you about, I'm going to hurry through all this because I know Deepak wants to talk more signal processing theory with you. I know you need to hear more of it. So I'm going to rush through some of it. No offense. So I want to share with you some of the work done by this smiley young guy here. This was his bachelor's degree honors thesis that they did in our lab. And it was something where we were trying to decide what sort of project he should work on. He thought coming into the lab that he wanted to be a physician. The goal was to go to med school, become a surgeon, make lots of money. And he was a very bright, very smart student. But we told him on the front end, we'd rather you become a researcher. We'd rather that you use those brains to make good scientific impact and good innovations. And he wasn't convinced, but by the time he graduated, he switched his focus and has been working in a startup company actually for a number of years and is now looking to go into biomedical engineering for master's training. So we think that was a win for science and for engineering and maybe a loss for clinicians, but that's often the case that we have students come in wanting to be physicians, and then after the research experience, they change their mind and want to go for a PhD instead, which I feel pretty good about actually. So what he used was something called a myoband, and then a modified obstacle avoidance game to test some general ideas about motor learning that we were testing out in the lab. So he wanted to combine all of his interests with other things that were happening in the lab itself. So a myoband is this system, essentially a cup array of electrodes that has been developed by a company spun out of, let's see which university is it, University of Waterloo in Canada, in Ontario. They spun out this company that's now called Biomechanics Labs, and they make this cup array. It also has an IMU inside one of the systems, so you can get accelerometry and rate gyro information from the arm, similar to what was displayed from the students in Delhi yesterday. But this is something where you can slip the cuff onto the arm, and you don't have to worry about the electrode placement per se, because you're getting basically the benefit of crosstalk in this case, where you can pick up signals in a radial sense all around the arm. So this is an interesting situation where you get fairly messy data, but you can also use that data with some of the in-house signal processing that the company provides, as well as your own processing of the raw data, to come up with different control interfaces for how to use your mouse, how to change the radio station on your car as you're driving. And the company has all of this shareware that it's put out so that people can develop their own interfaces for the data to control things in their environment, as long as they have access to some way to change the keystroke or the mouse click or some other analog interface. And so then the game that we modified, have any of you played this game? Have you seen this game before? Only one honest person, hand went up, okay, two, good. It's a very annoying game, but it's also somehow addictive. So you hate it and you want to keep playing it at the same time. So this was his idea, and he proposed this to us in the lab, and we said, that sounds just crazy enough to be fun, let's go ahead and do it. And he went for about 1.5 years of data collections and analysis and wrote it up, and didn't publish it, but had a good time with the data. So at this point, for those of you who haven't played the game, I want to just demo for you what it is, and you can begin imagining what actually might be a good therapeutic experience for this. So it's a very simplistic interface, right? And so the student that was working on this, he actually found a version of this on Scratch. I don't know if any of you know about Scratch as a coding interface for children. And he found a version of it there and did all of his coding in Scratch to make the modifications to the game so that it would follow his rules rather than the pre-written rules of the game. And this is what his intervention actually was. So for this game, you manipulate the bird by hitting the spacebar. So every time I hit the spacebar, the bird goes up, right? So then it's quite tricky to get through there. Not very good. So I'll try again. Oh, not very good. Okay. So, okay, that will come to a topic later. I won't show you more and more of my fails, but to my excuse, I'm watching that screen instead of this screen. So probably that's it. But okay, so I just wanted to show you that so you know what we're talking about. So we use the usual controller of the spacebar, or the usual controller is the spacebar or other keystroke you can code it for. But then he made an experimental controller then that's based on EMG activation that was based on a threshold pass to then trigger this flap or this thrust of the bird upward. So it's a very simple interface for him to basically code enough EMG has happened to make the bird flap. And so he went through a very brief calibration phase with the students that were being tested to make sure they could actually activate the muscle enough to make the bird go. But other than that, what he did was to experiment with these 3 motor learning approaches that we were experimenting with in the lab. One is that you would change the difficulty of the game in a linear fashion. So the thrust value would decrease, making the game harder, right? And gravity value would increase, making the game harder, because the less you're thrusting, the faster you're falling, and the more gravity is, the faster you're falling. It becomes very agonizing very quickly and very impossible to play the game. So he did this in a linear fashion, making it more increasingly difficult. And then also we coded in a random control where the thrust value changed between each game. And he would have them play like 30 games to have this intervention in a fairly pseudo-random fashion, so it wasn't exactly random. This made the game difficult based on the fact that it was totally unpredictable. So every time you started the game, you had no idea what gravity was going to be, you had no idea what your thrust value was going to be. So you had to very quickly respond to that in order to not run into a fight. And then he built up a very small AI to control the game. I put quotes around AI because it was more like just a set of rules that he wrote that would control how much overcorrection the game would provide for the user to make the game theoretically as easy as possible. So the idea was that every game that was played, the AI would store what the score was and what the performance of the person was, and actually change the rules of the game by the next time they played it, so that it would make it theoretically easier and easier and easier for the person to play the game, so they in the end could get the high score every time. So this was a drastic change from the linear increase of difficulty. And so to do this, he took a bunch of subjects, split them into these 3 groups. So he had pre-tests where he took them through some warm-ups and some calibration routines, and then took them through 3 basic practice rounds where they all played the same game. And then he split them into these groups and had them play by the Make Life Easy group, the Make Life Progressively Linearly More Difficult group, and then the Make Life Difficult by Randomizing and then making it an unpredictable situation. Then he tested them all again at the end the next day. So the idea was that they went home and remembered things, and they'd be able to show their learning effect the next day. And just clarify that he manipulated aspects of the game, so it's not the standard game. He would put in codes like this to train to even control the device, because a lot of people had not actually played this game before, surprisingly. And so they could practice by following this line, and he'd have them follow another line, and he'd have them follow these lines at different slopes. And of course, it's a bird going vertically, so it cannot fly on that line. So we would qualify basically how close to that line they were by pursuing the game practice. And then pipes, he made them generously far apart from each other, and just kind of had a series of up and down situations where the pipes got narrower and narrower, but not as random as the normal game is. So real quickly, as results, I will only emphasize this set of results over here. These are kind of pre-tests that he had done. But one thing you'll see, so the AI group is in blue, the line group is in orange, which was the linearly increased difficulty, and the random group is in gray here. And this is the difference in score between day 1 and day 2, with fairly an arbitrary score, which was just the distance traveled for the game. So one thing you'll see is that there's large error bars, right? But then qualitatively, there's some interesting differences between random, line, and AI. But if we focus on the variation that we saw there, the students started looking at why is there so much variation for something that was a relatively simple task and that we thought was responding very well. And so we started looking at the background of the people that were involved in the study, and he went back to his questionnaire that he had given them to what their history was with this sort of game. And we decided there were people that we called gamers, which were people who played a lot of video games. So basically your classic college student, right? Especially at the age and stage of when he was doing this work. These are people who spent their evenings playing games instead of studying, and they admitted it when they came into the lab for the research. So we subgrouped 15 students into that, and then we had a group that basically were terrible at the game. As you might have noticed, I was one of those actually, because I was in number 3 perhaps in this group. that for whatever reason, could not figure out how to get the controller to make the bird do the thing, and it was awful, right? And it turned out there were 7 others, not just me, which made me feel better. And then, luckily, the largest group were people that were not historically using a lot of games, but also not terrible at it like I was. And definitely this group, on average, was older than the rest of the group. This average group was, particularly in their 40s and 50s. Not particularly in their 19 to 22-year-old sort of thing. Stereotyping quite a bit. So once we split them into those 3 groups and looked at just the general group's performance, then we found something that was very interesting, is that the AI subgroup within the general subsample performs about the same as the line group as far as their second day versus first day performance, and that the random group actually performed significantly better than both of them at that point. So this was interesting because this was not necessarily what we expected. We expected that the AI group, which was making the game easier and easier every time they played it, that the people would become so good at playing the game that they would be able to basically understand how to do it and not have failed all the time. The next day they would do very well. But it turns out that motor learning likes variation, and so the random group had a lot of different experiences while they were playing the game. They failed a lot, and they succeeded a lot, and they played every variation between those. So when they came back the next day and played the standard game, they were actually much better at it than the other 2. But this is in the general group, not the gamers and not the old people. So I think I mentioned this, but basically after graduation, we took a job with a company called Liquidwire, which was a 2-year-old startup company at that time out of an engineering school in Portland. And they were really interested in his thesis, which we thought was crazy because we thought it was just this silly thing that we had done for a fun study in the lab. But this company, when he called and interviewed with them, wanted to know every detail about his game, what he coded in, what his AI idea was, and everything. How he got the signal, what he did for signal processing. And this is a 21, 22-year-old physiology student who has never had an engineering course. And he was able to talk with him at a level where he was basically able to talk his way into a job, which I was very proud of course. And then more proud that since then he's going on to work on his BME. So pretty excited about it. All right, that's all I have for that. Just a very brief show of what we're kind of doing with some of this space and what other people have also been doing. I think there's a lot of things that have already been tried in this space, so it's a little bit overused, overworn, but I think that's because people have been using the same techniques. So I think there's actually a lot of potential to innovate into this space if you have any interest at all in how to get feedback into therapeutic regimens to make, especially kids that are used to interfacing with games and with screens, to actually get the most of therapy. So I think there's still a lot of space to be improved out there. All right, any questions? Any thoughts? Anybody want to play the game? I can bring it back up if you like. No? Okay. Yes? So for this game, we normalize it to that person's ability to make a maximal contraction. Yeah. Right. So we had a small phase where we actually took them through a calibration series to understand whether they could or couldn't activate the sensor enough to trigger a threshold. And then we basically moved that threshold down to what was like at about 70% of their maximal contraction ability. And the reason why we built it that way is every time we put it on to the person, we'd have a slightly different strength of signal. And then between people, some people just could not activate that muscle in a controlled fashion. So that could have been why they failed. We're a group of 8. But, yeah. Yes. And the calibration step will take 2 minutes maybe. So put it on, make sure it's actually reading with the Bluetooth signal, and then a cue would come up on his game to say, do this, do that, rest, do it again 3 more times, and then it would update the game structure based on that, and then it would just start playing. So everybody who came in to be tested, they would come in the lab and be out of the lab 10 minutes later. So it was not a long process. Sorry. It's hard to think. There's a lot of fans.
Due to the reflex reactions, the muscles, will there be any errors being contained?
Yes, possibly. So I don't know if I'd call them errors though, more like just different reasons to calibrate to the subject. So in the therapy situation, if I'm understanding your question correctly, if I have someone who really has a strong problem, the ability to control the electrical signal may be very compromised. So I need to calibrate to what their capacity is. And then as they improve, I need to recalibrate again to allow them to play the game. That recalibration can also be documentation of it. Does that answer your question?
In this game particularly, how many attempts were allowed for a particular subject? Because it's a game where even if you try multiple times, you would fail. And only, well, if you played for a longer time, then you would have a better chance of having the good score.
Right.
So, was this factory situation or was?
Yes, it was considered, and we actually chose to limit their practice. So we gave them just like 3 to 5 games of practice just to familiarize with the game. And we said, don't worry about your scores, just explore the space and learn how to control the bird. And then we had them do 30 games that were in the therapeutic or the motor learning structure. And our reason for that is we wanted people to be able to demonstrate the motor learning effects, not the practice effect. So if you practice the game again and again and again, eventually you will get better, right? But we wanted them to come in just however they were and have a motor learning response. Now the flip side of that is the gamer group came in with already a preset number of experiences that weren't playing this game, but were cueing them to be very good in that interface. So we couldn't quite answer that fully. Yeah.
Sir, other than better hand-eye coordination, what differentiates the gamers from the non-gamers?
What differentiated the gamers from the non-gamers? In the performance of the game, you're asking?
Like, why are they so much better other than the hand-eye coordination?
That's a good question. That's maybe deeper than what our study could reveal, I think. I do think it's hand-eye coordination primarily with that group. Also, just the familiarity with what amount of things can fit into a screen and the movement of the screen as well. Some of our older individuals that were tested, including myself, I'll move myself into that group, it gets a little bit distracting to figure out where the pipe is, and it's hard to concentrate on the bird or what to concentrate on. But the younger gamer group said that's not a problem at all. I'm used to having 500 things going on the screen and still know what my little cursor thing is. So the group that was non-responders, essentially they really didn't like the game at all. And it wasn't just the controller with the hand. We would actually, after they were done with the study, let them play the game with just the space bar, and they still hated the game because they couldn't make it work well. So I don't think it was so much a problem with the controller that we had with the musculature, because the fact that those people were just not suited to the game. So that might be something where we learn from that and say, okay, what sort of game do they do well, and what sort of thing can they do well with? So given my particular generation, maybe it's Pac-Man or Space Invaders or something. Any other thoughts, questions before signal processing? All right, good. Well, thank you for the attention, as always. Before I hand the mic over to Deepak, since I think a lot of you are leaving either tonight or tomorrow, I just wanted to take a moment to say thank you very much for coming to this thing, and also for your flexibility, because I know my travel schedule was not good, and that disrupted all of your lives. So I really, really appreciate the flexibility you've shown to be willing to change your schedules, because I think it's a bad thing for a single American to disrupt so many people's lives, and so I really appreciate the fact you're still willing and interested to come to this. And just want to thank you for being such a great group and great to interact as well.
After that, we have a form. And give back. Right after 4 o'clock. After tea, they come back, and my scholar will list out the questions. Back to the single one.
Okay, so let's go to the board. Right. Okay, so we have almost 45 minutes sharp, and you have already heard the bad news that you have to appear in an exam at 4 o'clock. so, but that's the part of the GIAN program you have to go through it. So I have prepared just like 10 sort of questions. So they are kind of bit easy, bit tough. So let's see how we do. And so yeah. So let's go. Let's start. Let's utilize the maximum. So in the morning session, we have reached up to the spectrogram kind of thing. So where we have this one time domain signal, which I can actually convert into the time as well as in the frequency plane, right? So so basically, it's kind of just quickly recap. So the signal something like this, and I have this kind of thing, right? So if, as I said, like so this is your time axis, this is your frequency axis. So as I said, generally there are no numbers over here in the MATLAB. What they do is basically the color, right? If you see, this looks like kind of an image, right? And this image is generally called a spectrogram, right? So you can see from one-dimensional signal, I could convert into two-dimensional signal, which is kind of a picture, right? And then I told you yesterday that recently a group has utilized the same method, and they have compiled all the spectrograms like this, and then they come up with kind of a 2D histogram. Histogram, 1D histogram. Everybody knows histogram. Okay, so it's kind of 2D histogram now, like based on time and frequency. So if I compile not many figures like this, you'll have a spectrogram kind of thing, which will be in 2D, like maybe this way, kind of this way, right? So, okay, so this was in the morning session. We have reached to this level. Now let us see what can be done. Okay, so if you remember, I said this is kind of a Heisenberg uncertainty principle. Like it's a very standard kind of equation you will find everywhere. It says delta T delta F is always greater than 1/2. What does it indicate? If I increase in time, I lose in frequency. If I increase in frequency, I lose in time, right? So I cannot have both, right? So, but let us try to understand is actually why Fourier transform is not able to give me the time domain information. What is the reason? We know, right? The time frequency, Fourier cannot actually give me the time domain information. It gives me a very clean frequency related signal. So what is the reason that Fourier does not give me the time domain information? Anybody in the audience? What makes Fourier transform to not to give me the time domain information? Because you need to understand the problem and then you will come up with a solution. Okay, so the answer lies in the equation itself. So you can still try to figure out what is the problem. So the equation says x of omega is equal to x of t e to the power minus st dt. So what makes Fourier transform not to give me the time domain information when I convert into frequency? Very good. It is an integration actually. If you see, if I remove this integration part, still I am in time domain. Right? If I multiply this signal to other signal, I have all the time points. What happens actually is when I integrate with respect to dt, all the time points I add, and I lose the time domain information. Right? Because the same output can come from anything. Like 2 plus 3 plus 6 also give me 11, while 5 plus 5 plus 0 also gives me 11. You got the point? Right? And what I receive is actually 11. I don't know whether it came from 553, whether it came from 632 or whatever. Right? So actually what happens is this integration actually does not allow me to actually, in fact, this integration does not allow me to have the time resolution because I compile all the time points and then I get only one value, which I don't know at what point in time it occurred. So now let us see what is the solution. So of course we cannot remove integration, that is for sure. Right? And the other thing, if you see, it is because of one more reason actually. There is one way I can actually have some time domain information if I still remain this, if I still keep this integration, which is from minus infinity to infinity, and I change something in this equation. What are these changes I can make? Did you get my question? Right. So because of this integration part, actually I'm not able to get the time domain information. Because after multiplication, I still have the time points. I integrate them with respect to time, and eventually I lose the time domain information. So how can I actually figure it out? How can I still get the time domain information? One way you already know is like multiply this with some time domain function, which is a window, and then segment the signal, but that has still some problem, which I told you, right? Fixed time frequency resolution. So now, what could be the one of those solutions? If you see, actually there is, yeah, anybody? Pardon? No, integration to आपको करना पड़ेगा, otherwise you can't get the energy of the signal. Right? So if you see properly, what is this function? It's like e to the power minus, j omega. Right? What is this function? It's kind of a infinite duration signal. Right? Sin omega t, cos omega t, they are infinite duration signal. So what is happening is, this is my signal. I am multiplying it with an infinite domain signal, and then I am integrating it. Eventually, what will happen? I will lose the time domain information because my signal will be always less than the infinite signal. Getting this point? Right? This is my xt. This is my sin omega t going this way. I multiply this to this. Right? I multiply this to this and I integrate. So my all signal will go off. I'll have just one value, which I don't know will correspond to which time. So this happened actually because of my wavic nature of sinusoidal function. Right? So sine wave, so generally you say always sine wave, right? So sine wave creates a problem. It's not the integration, it is the sine wave which is creating the problem. So what should I do? I need something which is not going to infinite but has a very small kind of nature, but oscillatory nature ideally. So what we call that? wavelets. Right? From wave, we want to come to wavelets. So you should know that origin of that word, wavelets. Nowadays, you will also see many fascinating words. I mean, recently I heard lecturelets. So if somebody is not taking a 45-hour of lecture, he is taking 10-hour lecture, he will post on YouTube and he will say lecturelets. It's kind of very long to coming to a very short time, right? So you can see a lot of lecturelets. So, yeah. Oh, okay. Yeah. You can give me. Thank you. So, so you got the point. So from sine wave, we are trying to move to wavelets. So the first thing what you will notice in the wavelet, the first thing, it will be a finite duration signal. That would be the first thing, right? Compared to this sine wave. Sine wave is not a finite duration signal. It's an infinite duration signal, which is causing problem to my signal actually getting into the one waveform, one value, right? So now, so let's talk of, so now you know the origin of the wavelets, why wavelets are needed, right? Now let us think how the wavelet can actually help me. And then we will go to the mathematical part of this. That is a kind of signal. Is that everything? Okay, so this is kind of a signal, right? Actually, if you see what I want, when I say what I want, what do I want from my signal? At what time, what frequency? That is my ideal case, which is impossible, right? So what I want up from this to this time, what to what frequency? That is what I can compromise, right? The problem in the short time Fourier transform is there is kind of a fixed kind of resolution. Like I took a window, I slide it across the signals, right? If you see, I mean, that is very intuitive. So one thing is very clear, that wavelet is not going to solve your time resolution problem, time frequency resolution. It's a principle. Nobody can actually resolve it. But the advantage of having this wavelet is kind of something like this. Okay, think of this way. If your signal is slowly varying, very slowly varying, what would you expect from, what would you like to have, given this limitation of time frequency, for a slow varying signal, what resolution you will need, what resolution you will expect to have higher? What would you want? Okay, let me rephrase my question. I have a very slow varying signal, very slow varying signal. Would you like to have for that signal high time resolution or high frequency resolution? High time or high frequency? High time. Everybody high time? How many high time? How many high frequency? Yes. See, low frequency signal means it's a constant signal. Even if you say me t equal to 5 minutes, it was 2, or if you say t equal to 10 minutes, it was 2, hardly matters to me, because it does not vary there. Just imagine something like this. Right? Just imagine like this. If I draw a DC line, let us say I take a mean value of this, I draw a DC line, and I say that this signal is 2 volt. Right? At any point of time, it is 2 volt. Even saying such a vague word, I am very close to the true values. You got my point? Even the error, even if I took the error, it will be so less. You're getting my point? So slow varying signal means even if I don't know what time it occurred, hardly cares. The reason is it's almost same everywhere. You're getting the point? Just try to think. If it is a slow varying information, it's a slow varying signal, whether you tell me it happened at 2 milliseconds or it happened at 10 milliseconds does not care, because it's same. Right? But it would be interesting here to say, even if it slowly vary, what frequency resolution was needed. Right? And let us say this case. What do I want here? High time resolution or high frequency resolution? High? Why? this happens at a very particular time. If I take a longer window here, I don't know because it happened exactly at this point. Because if I take a longer window, it will dilute my window. Because I will say this happened almost from here to here. But if here I take a smaller window, it says me exactly at this point of time it happened. I don't care what was the frequency, because this is something very unique. You got the point? Right? Now just imagine something like this. Let us say this is a signal, right? If I apply a short time Fourier transform to the signal, I have one choice, right? I have one choice. If I take a bigger window, let us say I fix this kind of window, that is suitable for this person. That is suitable for this person, but not suitable for this person, right? If I take a smaller window, because I slide it this, so I will dilute this. Right? If I take a smaller window, something like this, right? It is good for this window, good for this part of the signal, but not good for this. So did you get the problem of short time Fourier transform? Right? Now I need something which can give me the multi-resolution capability. Just imagine that a signal is moving from like to like this here. Right? Just imagine that your signal starts from here and it goes like this. And just imagine that wavelet is kind of this thing, a lens. Right? I am moving. Here I says no, I want higher time frequency. I go there. Then I come back. I says no. Here I want more time resolution. I go back. You got the point? Right? So it is my choice. Although remember, I am not solving the problem of time frequency. It is still there. Right? But what I am doing is I am having a multi-resolution capability. Do I need a smaller window? Do I need a larger window? From here to here, when the signal is going on, I have a lens which has a capability of either zoom in or zoom out. Right? And what is this lens? Wavelet. You got the point? But remember, ultimately the point is, whatever transformation I do, I need to get my original signal back. Then only I can say transform. If I am going from this domain to this domain, and I'm not able to come back from this domain to this domain, this is not a transform. Right? Is that clear? Now, what does it mean? It means that wavelet should have the reconstruction ability as well. So I have lot many codes on wavelet which I can show, but I don't know I have time or not. But let me at least theoretically I can show you that how does it happen. Right? So if wavelet is a very good tool to actually zoom in between the signal. Let us say signal start from here to here, and I'm running like this, and I suddenly feel, oh, it's a high spike. I need more time resolution here, and I go and I zoom in there. Suddenly I come back, and it's a slow varying signal. I don't need more time resolution. I go back here, and I say I need more frequency resolution. Then I move here. I see, oh, again a high spike. Let me go in the time. Are you seeing what I am doing? Going time to frequency whenever I need as per my interest in the signal. And generally, you will see in all the signals, any event which is of importance will be kind of a spike. Means the important information in the signal will be for a very short duration, very short duration. So if you miss that short duration information, you're gone. You will be diluting that information if you take a larger window. Right? Because that larger window will say this event happened between this to this somewhere, which may not be that important, rather saying this event actually happened at this time, which is very critical to know. Right? So if wavelet can actually do it, what kind of property should wavelet have? Because you cannot make any random facts and oh, this is my wavelet. Right? So what do you expect from the wavelets? No. So let me show you what actually I want actually. So now what I want is, let us say this is my signal. Now what I want is that I have a wavelet. So the first feature of wavelet is the very first feature. Yes, the very first feature when I say wavelet should be, it is short duration. The very first feature, right? Now this very first feature, so right now let us assume, I mean I will tell you how the wavelets are constructed, but let us say I have a wavelet something like this. This is a wavelet, right? But you cannot make a lot of, I mean, by your own thinking that this is a wavelet. Wavelet has to spice some very important properties, right? But assume that right now this is a wavelet, right? So what I will do is, I will run this wavelet across my signal. Let us say I did this. So what I will do, I will take the coefficient between these two, exactly like Fourier transform. Exactly, like multiply these two signals, see the outcome. If this signal matches to this waveform, it will be high value. If it does not, it will be a low value, right? Then I will keep on shifting it like this. Fine. Next time when I run this wavelet through my signal, what I will do, I will change its scaling. I will either narrow it, either I will stretch it, right? Let us say I actually narrow down. So what will happen? It will become something like this, right? I will again run this waveform across this. If there is a very sharp peak, very important transition in my signal, this will capture it. It may not be able to capture it, right? Then I will again run, right? Then what next? I will expand it. I will do, and then I will again run. So you know what I am doing? By this wavelet, I am trying to capture all the slow varying components in the signal as well as all the high varying components in the signal. And what are the slow and high varying? They are just the frequency. Slow frequency, low frequency, and high frequency. Right? So what do we expect that what kind of equation will be there for the wavelet? Equation कैसा दिखेगा wavelet का? This silence is not good. Pardon? So what, like for example, in the Fourier transform, you have x of omega. What do you expect here? So it will be something like this. So do you know what I am doing? What are my variables? A and B. So once, let us say, let's try to do this. Let us say, and this is called mother wavelet. Later I will discuss the father wavelet also. Let's talk about mother wavelet first. So we have this mother wavelet. It can be anything. I will tell you what are the properties it should have. But let us say this is my mother wavelet. So let us say what I am doing in this, because this is fixed almost. It's not changing much. What I am doing in this, first I am taking my mother wavelet. First, let us say A equal to 0 and B equal to 1. Right? What I did, I took mother wavelet, right? And I run it and I found what are the coefficients. Next time what I did, I changed my A. Earlier it was 0, now I did 1. Once I do it 1, what will happen to this wavelet? It will go like this. So earlier I multiplied, let us say this was my wavelet. When A equal to 0, B equal to 1, I multiplied these two and I get a value here. But that value is corresponding to A equal to 0, B equal to 1. Right? Next, what I did, B I still remain the same. A I said 1. What does that mean? It's shifted here. Right? What I did, I again multiplied these two, whatever value that is corresponding to. Fine? Right? Similarly, I put 2, 3 equal to, and it will go like this. Right? Next, what I will do is, I will put B equal to 2. Right? So now I will put A equal to 0, B equal to 2. So means now this is not being multiplied, the scalar version of this is multiplying like this. Right? Then I will multiply it. Same thing, I will shift it. So what will happen? I will get a kind of matrix like this. And there will be a lot of values. So this is A, this is B. Now if you practically see, what is my A? Although we are calling it scaling, but what is A practically? Oh, sorry, not A, B. What is B practically? What is that? Yeah, what is width? Yeah, so changing width means what? Changing width means changing frequency. Right? If I change the width of this, what does that mean? I've changed the frequency of this. Earlier it was this one cycle was for this much time. Now this cycle is of this much time. Means I have changed the frequency. So I'm calling it. So A is generally in wavelets family. A is called translational parameter and B is called scaling parameter. Just to avoid any conflict of interest with the Fourier transform. Otherwise, this A is nothing but a frequency information. Sorry, B is nothing but a frequency information. You got this point? Okay. This is the theoretical concept of how to do the wavelet transform. Now, as I said, what would you expect? Like, can you make any waveform? There are only like, I think less than 20 wavelets right now. So what stops me to create more wavelets? Why can't I make my own signature and say, hey, this is my wavelet? Because my signature are also finite duration. What stops me? Very good. You can't make any wavelet. You can't say this is my wavelet. You try and you will fail. That's why across the world, so many scientists and we have still like I think not more than 20 wavelets. Because each wavelet has to satisfy all the properties that was satisfied by these basis functions. Do you know what these wavelets are basically? They are the same like sine and cos. Right? They are making the basis. But now the point is in this room, I have lot many bases. How do I get lot many bases? One, by scaling them here and there, right? And second, by translating them. So that's why you call mother wavelet. Means this is a mother wavelet. By diluting or strengthening the signal, I get all the babies. By shifting them, I get all the babies. So it is a mother wavelet. Right? This is called the mother wavelet. They actually derive all these families. So assume that I have now lot many families in this room. Right? Means one mother wavelet and I can make infinite. Right? Now the question is, how do I derive? How do I say this is a good wavelet? I mean, whether it qualifies for a wavelet or not. Because I need to prove orthogonal and orthonormal property. If I can't, then it's of no use to me. Right? So I'll give you an example, which was the first wavelet derived, and which is not so useful sometimes. Even though in one of our paper we found it better than other wavelets, but to be very honest, it's not so good. And you have to tell me why it can't be so good. Right? So let me draw the wavelet first. So the very simple wavelet is, which was the first one to be developed. Have you heard of Haar wavelet? How many of you have heard Haar wavelet? Yeah. So actually it is the most popular wavelet developed, and it is kind of something like this. Simple. So it qualifies the first property. What is the first property? Finite duration. Right? This is the first property. Now I need to prove it is orthogonal to its babies and it is orthonormal to itself. Right? So orthonormal means what I will do? I will multiply this to this and I will integrate, it should come 1. So if I multiply this to this, what will happen? This will go up. It will become a rectangular with 1 here. So what is the output? 1. Fine. And if I shift it by 1, the other wavelet will be like this. So this is one wavelet. This is one wavelet. If I multiply both of them, what is the output? 0. Because it has nothing. It has nothing. Here it has nothing to multiply. It has nothing to multiply. So it's 0. Right? If I put another wavelet, shifted wavelet, same thing. Right? And if I put half of this, what will happen? This half will come positive. This half will come negative. It will cancel itself. You got the point, right? So Haar is a very simple wavelet to understand, but practically it is not so useful. Do you know why? Okay, can you tell me any case where Haar wavelet can be very useful, but not others? Are you getting the wavelet actually? Are you understanding the concept? I don't know. Yes, we will see in the exam. So tell me, in which case Haar wavelet can be very useful and in which case it won't. Yeah, I'm talking in terms of a signal. For which kind of signal you feel Haar wavelet can be very useful, and for which kind of signal you feel that Haar wavelet will not be useful. Should be very simple to answer. Huh? What is your logic for binary? Because your answer is close, not exactly correct. Yeah. So his logic is correct, although the answer is not that correct. So just imagine, you don't have to do mathematics all the time, just common sense. What I have to do is basically what I'm doing. How much of this characteristic of this signal matches to my signal? If it matches perfectly means it will give high value. If it does not matches means it will not give me high value. If you see the shape of the Haar wavelet, it's very sharp, right? Sharp features. So if my signal has very sharp features, like you said, it will easily capture those. But if my signal is kind of slowly varying, like a sinusoidal, it won't capture. Did you get this point? Right? So that's why Haar wavelet is not so many of the time Haar wavelet is not useful because it can only capture the sharp transition in your signal, very sharp signals. Otherwise, if they are a smooth characteristic of your signal, it won't be able to capture. Right? So you need to know what kind of wavelet you are applying. So that's why I'm telling many of the papers you will see that they will apply hundreds of wavelets and they will compare, but they don't know why this result was good, why this result was bad. So you should be able to go back to your logics after the results, whether my results are matching with my logics or not. Right? So if you see Haar wavelet feature, if in your signal these kind of peaks are there, then of course Haar wavelet is very, very good. But in biosignals or any kind of signal use is very rare. So even Haar wavelet is now kind of obsolete other than in teaching. Because in teaching it is very easy to teach somebody that Haar wavelet satisfy all the orthonormal and orthogonal properties. Right? So that's why when it after almost 10 years of this wavelet, there was a professor in Stanford who actually developed the Dobichov wavelets. So they are very popular. They have D1 to D20 wavelets almost within the family, which qualifies all the conditions for a wavelet. So they looks like, I'm just drawing it. Don't go with my drawing, but this looks something like this Dobichov wavelet. Not sinusoidal, but it looks something like this. So the idea is, can you make a wavelet which have sort of sharp transition as well as smooth within that waveform, plus it satisfies the orthonormal and orthogonal properties. So now you imagine with this much of restriction, you can't create a lot of wavelets. You got the point? Right? That's why there are only limited wavelets available to us. But you can try, if you are a good mathematician, you can try to develop new wavelets. Maybe you say that, hey, I have developed this wavelet which is very, very useful for only the EMG signal, which are very, very useful for EEG but not for EMG. But that needs a very rigorous mathematics because you have to, at the end of the day, prove that they are really orthogonal and orthonormal to their baby's family. Right? So now, okay, so we have a few more minutes, so let us see. So now this question comes that does it make really sense to do all this? I mean, although it's very ideal kind of situation where you have a lot of values and you can like do a lot of things. I mean, make a wavelet, run it across your signal, change the width, run it across the signal, change the width, keep on running across the signal, and you get a big matrix, and that is definitely very helpful. But does it make really sense to you that okay, should do this, or do you think no, we should think something else? What would be the problem in this type of case?
Other than ECG, EMG, EEG are not theoretical.
No, ma'am. Huh? Very good. Yes, very good. So, although it is an ideal case, this is a perfect ideal case you can analyze here. Just imagine that you have all the frequencies all the time. I mean, just imagine a matrix full of this room, and you want to zoom in at any point of time. You go to that corner, you go to that corner, you go to that corner, whatever you want. But imagine storing this kind of matrix, and then, like you said, computational power, keep on running, and you have infinite possibilities, right? You can go to any scaling, any stretching, any shifting, like all these things. So the idea is, although it's very good, and this is, I mean, it's not that people are not using it, For research purpose, people are still using it. And this has a very common name, which is called continuous wavelet transform. This is called continuous. What I explained to you was continuous wavelet transform. CWT. Right? If you search in MATLAB, you will find a command CWT. Right? And it's a very nice figure. I mean, if you see the figure and you feel, oh, my paper will definitely get published if I put this figure. So beautiful. But the problem is that the point is, like, in the real time, it's very difficult to get these kind of imagine that can your Arduino perform this kind of function? Even your Raspberry Pi can perform this kind of function. Of course they can, but by the time they do it, it will be like a lot of delay. Right? So here comes a very interesting theory which somebody actually developed. The same professor, Dobichov's PhD student actually developed this, and he come up with a very interesting logic. Now he says that the same information you can get by just applying some filter banks. Have you heard of filter banks theory? Naam to suna hoga kam se kam. Right? At least you have heard the name. So whenever I am teaching in North, I used to say some Hindi dialogues, but I think they are not useful here. So. So there is a very Hindi famous dialogue, that naam to suna hoga. How many of you heard of this? Yeah. So same filter banks ke liye we say same thing. Naam to suna hoga. Even though you don't know, but naam suna hoga. So filter bank is a kind of theory. We apply a lot of it. So it's kind of, I don't know how much I can explain. But just imagine that this is your signal, right? Earlier, what you are doing, you are running through a wavelet across the signal, and you are getting a lot of features based on whether it is small wavelet, whether it is this. Now this guy has developed a very interesting theory, very low computational kind of thing, and almost gives the same information. Of course, not exactly like this. What he says is, have a signal, right? Apply a filter here of half at the above, half at the low. So for example, you acquired your signal at 100 hertz, right? So what you do, take a signal, split this signal from 0, make a two filter, one from 50 to 100, second from 0 to 50. Because you have filtered the signal, so what do you expect now? What do you expect now? Your frequency resolution will increase. Because earlier you were saying in the entire signal that I have 0 to 100 hertz. Now you are saying I have only 0 to 50 hertz. Now if I further do, I will say only 0 to 50 hertz. But remember, while you are doing all this process, your coefficients will also decrease. Coefficient decreasing means you will lose the time resolution, because you are increasing the frequency resolution. So here, when I have the signal, what is high, time or frequency resolution? When I am having the original signal with me, what is my time resolution? When I am having, before doing the wavelet, when I am having my signal originally like this, yes. So when I am having the signal in the original signal, it has infinite time resolution. What do you mean infinite resolution? I know at every point of time what is the signal. I don't need to say that from this to this the signal was 2. I will say at t equal to 0 it was this, t equal to 1 it was this kind of. And same thing happens when I almost do the wavelet, doing wavelet transform, and I reach at the lower end, I exactly know what is the frequency. But the problem is, by the time I don't know where is that frequency in my signal. Right? But the point is, from going here to here, you have different images. You can select which image you want to select. You want higher time resolution, go up. You want higher frequency resolution, go down. Right? So again, it is the same thing like this, multi-resolution capability. But I did not run my waveforms. Like computational power reduced, right? And of course, the structure is very nice. You can have some interpretation of the data. So it looks like something like this. I don't know whether I can finish or not, but just let me give you a try. So the signal actually looks like this. You apply a filter. So this is a high pass filter. This is a low pass filter. Right. Something like this. You have the original signal. You just, for example, your signal was from 0 to 100 hertz, for example. So you apply a filter of 50 to 100 hertz and 0 to 50 hertz. Fine? Get the coefficient here. Similarly, you keep on doing like this. So when I apply a low pass filter of 0 to 50 hertz, means the output will have now only the frequency from 0 to 50 hertz. Means my frequency resolution actually increases. Earlier I was talking of a bigger range, now I am localized 0 to 50 hertz only. Further I do means 25 to 50 and 0 to 25. So I get some coefficient. And I can go up to whatever level. So what will be the level? 2 to the power n. Right? And in the end, what will happen? I will have the highest frequency. I know exactly what frequency, but by the time I will have only one coefficient. It means that I know what is the exact frequency, but I know where in the time. This is called exactly the wavelet transform. Discrete. This is discrete wavelet transform. And mostly it will be used in the research paper or mostly in the real life. But of course, CWT, which I said continuous wavelet transform, is still being used for many applications where you actually need a very high resolution kind of thing. But this is discrete wavelet transform, DWT. Right? So this goes like this. But generally, we don't prefer to actually go further in this direction, high pass filtering. Why? We generally don't prefer to do the same branching for the signal which is coming here. Although we do, but very rare. Generally, we stop here, but we keep on going there. No. Because this is high frequency. What do you mean by high frequency? Spike. Right? For the spike, there is no sense in going for this side because when I'm going there, time resolution is decreasing. Are you getting this point? So the best time resolution I can get for high frequency is almost this. Are you getting my point? Further I can go. I'm not saying you cannot go. You can absolutely go, but that does not make any sense to you. That will not give you any additional information. Why? Because if I'm going high frequency, so for example, now at this case, I'm doing, so for example, in this case, I have a window like this. If I'm going further, for this, I am increasing the window. Of course, it will come there also, but that does not make any sense. Because if I get the better resolution here for the high frequency, why should I go for a lower time resolution for high frequency? You got this point? Right? But here, we need to go. Because it's a low frequency, so I can have where exactly it was. And the further that even if you can go here, as I said, it's not that you can't go. And when you make this kind of thing, when you make this kind of thing, it is called, anybody knows? When you do symmetrical, like for everything you want the time and frequency resolution. What is that called? Yes, very good. Wavelet packet tree. This is called wavelet packet tree. Got the point? So actually, again, I will tell you very, very clearly, wavelet does not solve your problem of uncertainty in time and frequency, and it can't. The only thing that it gives you is basically the multi-resolution capability. That's it. It also cannot give you at the same time that what was the frequency and what time what was the at what time what frequency was. The only thing you have the flexibility in wavelet is you can zoom as per your requirement. Just imagine that in short time Fourier transform you have a fixed, you only go like this. But in the wavelet, you can either go there, you can either go there, based on what you want. Is that clear? Right. So sampling frequency plays a very critical role in this. So I don't know because it's already time is almost over. So I would like to show you some MATLAB code, but that's not possible. He's already from there. Stop. So if you have any question, feel free to ask me. Oh.
What is the benefit over normal frequency?
No, if you go to the extreme end, so you are right. So if you go to the lower end, you are exactly doing the Fourier transform. It is very well said. At the very top end, you are exactly in the time domain. The wavelet is beautiful only in between. At the lower end, you are exactly in the time in the Fourier transform. So extreme end of your wavelet is basically the Fourier transform, and the top end is your time domain. Because at the end you will have only one value, right? So one value means you know the figure, but you don't know where is the time. Same like in Fourier transform. But Fourier transform gives you from here to here. Wavelet gives you like in between. What do you want? Yeah. Actually, this process is very simple. If you use machine learning to do this, that will be like abusing the machine learning. This is very straightforward. You have multiple filters. You keep on applying the filter, you get a very nice time frequency resolution with every filtering stage. You lose the time resolution, which is very intuitive. You lose. Nobody can stop that. But now the beautiful thing is you can find at what time resolution, whether you are interested in time resolution or frequency resolution. You decide. If you want time resolution, go up in the branch, go up in the tree. If you want frequency resolution, go down to the tree. Any more questions? Fine. So the questions that I've given to you are exactly related to what I've taught in last 3 days. So if you can solve it, that's great. If you can't solve it, we'll see that what we can do. So I would request if we can take these 2 students out of that exam, because there is a conflict of interest. They might know a bit of this, but it's up to the coordinator. So they are these IT students, so they might know few of the questions already. So I don't want to have a conflict of interest. So